In previous lectures we talked about the gravitational force and the normal force. Today we're going to talk about the friction force. The friction force and the normal force have a similarity in that they're both forces that the surface exerts on the object on top of them. In the case of the static friction force in particular, that's the force the surface exerts when we try to take the object and slide it across the surface. We can understand the physical origin of this force with a simple picture. F sub s is the term we use to denote the static friction force, by the way. But let's consider a box resting on a floor, for instance. If you zoom in on the box and the floor, you would see that the surface of the box and the surface of the floor contain microscopic irregularities. And at rest, the box would fit sort of inside these crevices of the floor. And if you were to apply a force to the box, trying to make the box slide across the floor, the crevices of the box would make contact with the crevices of the floor, and the floor crevices would exert the force in the opposite direction, and this force we call the static friction force. We would like to mathematically model this force a little bit there. I'd like to know how the force behaves, what things it depends on, etc. So let's consider just a quick experiment. Suppose I'm standing here and I want to move this table across the floor. If I don't exert any force at all on the table, then we can reason that the static friction force must be zero. Otherwise there'd be an unbalanced force and the table would accelerate somewhere. If, on the other hand, I do exert a force on the table, just a small force, maybe a 10 Newton force, and the table doesn't move, we can reason that the static friction force is no longer zero, but is equal and opposite to my applied force, so negative 10 newtons. If I exert a force of, say, 20 newtons on the table, and the table still doesn't move, then we can see that the static friction force must have increased to match my applied force, so now it's equal to negative 20 newtons. So far we can see that the static friction force is actually a variable force whose magnitude depends on the applied force trying to get the object to slide. Alright, but the static friction force can't continue to match the applied force forever, because from experience we know that if you apply a sufficient force, you can actually get the table to start moving. So that tells us that the static friction force can vary between 0 and some upper limit that we'll call F sub s max. We would like to mathematically characterize this maximum static friction force as well. And again, we can go a long way if we just think about it a little bit. So, for instance, suppose we change the surface that we're trying to slide the table across from ice to asphalt. We can intuit that the force required to slide the box or the table across the asphalt surface would be harder or larger than the force required to slide it across the ice surface. And the reason for that, we can look at our picture over here to sort of infer. So the difference between ice and asphalt would be this. The asphalt surface would have a larger number of crevices. The crevices would be thicker and stiffer and also probably deeper. All that to say that the asphalt surface would be basically rougher than the ice surface. So we can reason that the static friction force should increase in proportion to the roughness of the surface. Which in turn reflects basically the number, size, and stiffness of the crevices that are in contact with each other. We have a single mathematical parameter that characterizes the roughness of a surface, and we call that the coefficient of static friction. And this coefficient is denoted by the symbol mu sub s. So, since it characterizes the roughness of a surface, mu sub s would be 0 for a perfectly smooth or slippery surface, and as the surface got rougher, it would increase in proportion. For typical situations like feet in contact with carpet or rubber on road, mu sub s is something on the order of 0.5 or 1 or 2 or something like that. But we'll just summarize all that by saying that mu sub s is some number on the order of 1. Okay, there's one more thing that the maximum static friction force depends on. So for instance, if you were to park a car on top of the table, then you can easily imagine that it would be quite difficult to get the table to start moving. And the reason is, if we go back to this picture over here, that if you park a car on the table, then you have a larger force pushing the table into, or the box into the surface. It's going to push those crevices together more tightly, and it would be even more difficult then to slide the box across the surface of the floor. Alright, so the maximum static friction force should depend also on the force pushing them together, the two surfaces together. We've actually already encountered this force. The force pushing the two surfaces together is none other than the normal force that we talked about previously. So, Fs max would be proportional to that force pushing them together, Fn, and also the roughness of the surfaces. And we can combine these two proportionalities into a single equation and say that F sub s max is equal to mu sub s times Fn. Alright, let's apply this to a quick, simple example. Suppose you're a basketball player sprinting down the floor. We'd like to know what maximum acceleration you could have. Clearly, I think we can infer or intuit that the maximum acceleration is dependent on the roughness of the surface. You can go faster along asphalt than you can accelerate faster along asphalt than you can along ice. So, suppose the coefficient of static friction is something around 0.6. We'd like to know what your maximum acceleration is. Alright, well, to figure this out, we simply have to draw the forces acting on our person. And we have 3. We've got gravity, as always. And then since the shoe is in contact with the floor, we have a normal force. And if you think about it, we also have a static friction force acting between the floor and the shoe. And that's because when you're running, you plant your foot on the, or plant your shoe on the floor, and to push yourself forward, you have to try to push your shoe backwards. And the act of pushing your shoe backwards will make the floor, via the static friction force, push you, or your shoe, forwards. So, you have a static friction force going in that direction. To get the maximum acceleration possible, we'll just fill these into Newton's second law. In the x direction, we just have F sub s. We're interested in the maximum acceleration you can have, and that would be given by the maximum static friction force. The maximum static friction force is given by mu sub s times Fn, as we said over there. And therefore, A max would just be given by mu sub s times Fn divided by your mass. Now, to figure out what Fn is, we always have to apply Newton's second law in the y direction. In the y direction, we have Fn minus mg. Acceleration is roughly 0 in the y direction, and so that tells us that Fn is equal to mg. And if we plug that into here, you see that A max is equal to mu sub s mg divided by m, and that just works out to mu sub s times g. If we fill in the numbers, 0.6 for mu sub s, that'd be approximately 5.88 meters per second squared.